Hi everyone and welcome back to my YouTube channel, and in this video we are going to discussing about the transformers and its in-depth architecture. And this video is a combination of the Hindi and English, but most of the time I'm trying to use the English word. And this is the most important part while you are trying to building any GPT model or building the LLMs model. So without wasting the time, I am going to start a tutorial now. So what is actually transformer? If you are from Tripoli or a electrical background, maybe the transformer word vary. But if you're from engineering faculty or you learn machine learning or deep learning or data science, you know about the transformers. So transformer is nothing but a neural network architecture that's have been gaining popularity right now. Recently, Google launched their artificial intelligence chatbot that's called Gemini. And also OpenAI recently launched their chatbot, or you can say the AI LLMs model that's called ChatGPT. So in the back end, they're actually using the transformers. Yes, transformers. Now the question arises, why should you use the transformers? I assume that you know about the RNN. RNN means recurrent neural network. But even we have the RNN, but why should you use the transformers? We know RNN actually work on the textual data and also the transformers. But why not RNN and why transformers? Because RNN cannot put the input in a parallel form. And also RNN don't have any memory, so that it can't memorize anything. But in LSTM, it's may have. But why not LSTM? Why transformers? Because we know LSTM means long short term memory. That's mean LSTM has memory. But the problem is you cannot put the input as a parallel. And also it's take much more amount of time in order taking the data and also training it. That's why we're using the transformers. समझ आया ना? समझ आया? अच्छा से बोलूंगा, सुनो एक बार. RNN means recurrent neural network. ओके, RNN पर तुम पैरेलल इनपुट नहीं दे सकते, इसका बात वहां पर मेमोरी भी नहीं है. ओके फाइन, लेकिन LSTM पर तो है ना. लेकिन LSTM बहुत टाइम लेता है, बहुत टाइम लेता है ट्रेनिंग करने के लिए. तो इसलिए ट्रांसफॉर्मर आया है सीन पे, राइट? क्योंकि ट्रांसफॉर्मर टाइम नहीं लेता, इतना टाइम भी नहीं लेता. यू कैन यूज द फ्रॉम द हगिंग फेस ऑल्सो. सो दैट्स व्हाट ट्रांसफॉर्मर इज कमिंग. आप देखो कितना इंपॉर्टेंट है ट्रांसफॉर्मर, बहुत अच्छा है ना. तो हम लोग जाएंगे यहाँ पर ट्रांसफॉर्मर के इंडेप्थ आर्किटेक्चर देखेंगे और कैसे काम करते हैं ट्रांसफॉर्मर. देखो, ट्रांसफॉर्मर इज नॉट ए न्यूरल नेटवर्क, इट्स ए न्यूरल नेटवर्क, बट इट्स नॉट ए रिकरेंट न्यूरल नेटवर्क. It's actually working on attention base. We know that we have the back propagations or the forward propagation like that. Yes, it's happening. So जाते ही यहाँ पर और in-depth architecture डिस्कस करते हैं कैसे काम करते हैं ट्रांसफॉर्मर्स, राइट? पेन और पेपर लेके बैठो, राइट? दिक्कत की कोई बात नहीं, फॉलो करो मुझे, बहुत अच्छा अच्छा वीडियो बनाऊंगा. लेकिन आपको सब्सक्राइब भी करना पड़ेगा, लाइक भी करना पड़ेगा, बहुत सब्सक्राइबर कम है. ओके, बिना किसी देर के स्टार्ट करते हैं in-depth आर्किटेक्चर ट्रांसफॉर्मर का. सो देखो, मैं एक ब्लॉग से पढ़ाऊंगा a transformer. I just wanted to learn from it here, and I also teach you out. So transformer hai kya, and why should you use the transformer? Let's say you can see one input. It's in maybe in the French or Spanish language. I don't know. So it will put the transformer, and transformer give me one output. I am a student. That's mean transformer may be used in a textual data, and also it can used to do the speech to text and also the language translation, right? That you can see you can give the language in another format or another language it will give in an English language. So this is how transformer actually work. Now we are going to see the in-depth architecture, how it is actually happening, what kind of layer, what kind of encoder and decoder actually inside your transformer layer. See, transformer is actually working in a encoding and the decoding format. See, in a transformer it have on encoders and also on decoder. यहाँ पर एक encoder है और दूसरा है decoder. तो तुम RNN के बारे में तो जानते हो, राइट? RNN पे की एनकोडर और डिकोडर है, लेकिन इट्स क्वाइट डिफरेंट. द आर्किटेक्चर ऑफ द एनकोडर इन द ट्रांसफॉर्मर एंड आर्किटेक्चर ऑफ द एनकोडर इन द RNN quite different. No problem. When you go deeper, we can understand what actually happening inside this transformer encoder and the decoder. See, when you break down this transformer, it have one encoder and another decoder. Now you are going to pass your input, I mean your Spanish language or Hindi, whatever else, you pass it inside your encoder, and this encoder pass this input to the decoder, and decoder give me the output. Now the question is, what is happening inside the encoder? Encoder के अंदर क्या हो रही है? वो जानेंगे हम लोग। ओके, नीचे आते हैं हम लोग। देखो यहाँ पर एक एग्जाम्पल है। द एनकोडर कंपोनेंट इज a stack of encoder. Stack है last in first out like that. The paper stack 6 of them top of each other. तो वहां पर एक पेपर की बात कर रही है, लेकिन वो पेपर है क्या? Yes, it's a research paper from attention mechanism, right? Let me see you. And this is the paper that's called attention is all you need. So इस पेपर से बोल रही है यहाँ पर some encoder और decoder है, right? It is the transformer architecture. So इस पेपर वो follow कर रही है, right? After that, it will building the transformer, right? Don't worry, you will get this paper link in the description. You can also read it out. All the things are same. All the things are same. Okay, so see one thing here. There are 6 layer of the encoder. Exact 6 layer of the encoder. That actually discuss about the paper. देखो यहाँ पर 6 encoder होना चाहिए. 6 encoder. क्योंकि वो बोल रही है पेपर पे. Someone actually call me that why should you don't use here the 8? Why should you don't use here the 12? देखो भाई वो रिसर्च कर लिया. Okay? वो रिसर्च कर लिया इसलिए शायद 6 is the best for one. That's why they actually use the 6. Maybe the 8 is the best for that. Maybe they use the 6 one, right? So that's why they actually use the 6 encoder. They use the 6 encoder. And after that, they pass the input. After that, they pass the input. Now the last of the encoder pass that data into the decoder. And decoder give them an output. Now let's go on the each of the encoder. What actually happening inside this encoder? So the encoder are the identical in a structure, yet they don't have the shear weight. See one thing. Encoder is nothing but the combination of the self-attention and one feed-forward neural network. We know about the feed-forward neural network. That's means it's सामने जाता है ना, सामने जाता है. Feed-forward neural network. And self-attention is an attention mechanism based on the attendance score, not attendance, attention score, it will give you an output. See, first what it will do, when you divide the transformer, we have encoder and the decoder, and when we divide this encoder and decoder, we have the 6 encoder and we have the 6 decoder part. Then when we divide this encoder, we have one feed forward neural network and one self attention. That's mean we know that transformer work on attention base, or you can say attention mechanism. Now the question is, what is actually attention? What is attention? Attention होता है क्या? Right? आगे जाते हैं यहाँ पर. The encoder input first flow through a self attention layer, a layer that has the encoder look at what in the input sentence as it encode a specific word. Listen again. The encoder input fast flow through a self-attention layer. It have one self-attention layer, okay, and a layer that have the encoder to at other word in the input sentence as it encode a specific word. That's mean when a sentence come up, it will give the attention, much more attention, right? Just like a girl. Okay, so यहाँ पर ऐसे काम करते हैं attention, right? So we will look the closer at the self-attention layer in the post. Don't worry. So see one thing, decoder has both those layers, but between in the attention layer that helps the decoder focus on relevant parts of the input sentence. See one thing, one important tip. In encoder, you have a feed-forward neural network and one self-attention. But in decoder, you have a encoder and the decoder attention, the middle of the in between feed-forward neural network and the self-attention. See, one again. We have the transformer, we pass the data in the encoder and decoder. When you divide the encoder, we have the 6 encoder and 6 decoder. But when we divide this encoder, we have the self-attention and the feed-forward neural network. But when you divide the decoder, we have one extra layer that's called encoder-decoder attention. Right? Encoder, decoder, attention. Pani peene do, actually. Let me drink the water. Okay, fine. So then we have the bringing the tensor into the picture. Let's see. We have this sentence J, Swiss, like that. So we divide them sentence into some tensors. Right? See, when you pass the sentence inside the self-attention, we are going to pass them into one kind of vector. It's one kind of vector, or you can say one kind of embedding layer. If you know about the NLP, you know what I'm actually talking about, the embedding algorithm. You can see embedding algorithm. So there are so many embedding algorithms actually available, like water vector, TF at IDF, vectorizer. So that's the NLP application in general, right? See, so that's when we divide this data or text into vector, one kind of vector. See, we divide them data in the vector. Then what I can do, we are going to pass the data in parallel again, again. See, first we divide them sentence. I mean, pass this sentence inside one embedding algorithm. It can be word to vector. Then we are going to pass this vector inside our self attention. See, we pass the data in the parallel, not one by one, but in RNN or LSTM, we pass the data in a one by one. But in here, we pass the data in a parallel. I mean, in a single pass. That means don't take much more amount of time. Here in RNN and also the LSTM, we pass the one data, then after this one, then after this one, right? But we in here we pass the data in a single, right? So that's why it's don't take any time. Now one question arises here: what are the size of the vector? They actually clarify that vector size is nothing but called 512. They actually divide this vector in the 512, right? Then what I can do, we are going to pass this vector inside a self attention. Now when you pass the data inside the self attention, it will give here one another output vector. Then what I can do, we can simply pass this vector inside our feed forward neural network. Now after that, what actually happen? See, when you're trying to actually divide this encoder, see one thing. See, we have two sentences like the thinking and another one is called the machine. So when we pass the thinking and the machine also, we get here jet1 and the jet2. Then we pass here the feed for all neural network. Again, we get here R1 and the R2. Then this is nothing but one encoder. यहाँ पर one encoder है, right? इसके बाद और भी एक encoder है, क्योंकि यहाँ पर हम तो देखा था ना 6 encoder है, यहाँ पर 6 encoder है. इसके बाद यहाँ से जाएगा यहाँ से जाएगा यहाँ से जाएगा यहाँ. That's mean what I can get? We can get X1, X2, X3, right? Okay, not this one. Yep, thinking and the machines. So we can get the Jet1, the Jet2, then R1 and the R2. Then we maybe get Jet1 prime, Jet2 prime like that, right? Now we see the attention at a high level. See, we actually discussing about the architecture of the encoding and the decoding. Now we're going to see that what is actually self-attention and why it actually very important role in the transformers. So देखो एक बात यहाँ पर एक sentence है. The animal did not cross the street. Again, the animal did not cross the street because it's so tired. Right? यहाँ पर बोला है animal did not cross, वो cross नहीं किया street को because वो थका हुआ है, right? तो इसलिए वो cross नहीं किया. देखो, so it means it किसको कैंडिडेट, I mean क्या बोलूं, it's actually indicated the animal, right? It is indicated to the animal. As a human being, we know that correctly, right? But if we put this sentence inside an algorithm, it cannot actually understand what is actually happening here. They maybe say that it may be the indicated in the triad, or it may be indicated to the street. As a human being, see that it means it was too tired. Who is tired? कौन थका हुआ है क्या ना? Animal. As a human being. But एल्गोरिथम तो नहीं समझेगा ना, इसलिए क्या हुआ, एल्गोरिथम को मुझे पास करना पड़ेगा. इसको बोलते हैं अटेंशन बोलते हैं. यहाँ पर देखो, यहाँ पर सेंटेंस है द एनिमल डिड नॉट लाइक दिस वे, एंड यहाँ पर इट से कुछ रे, देखो वो इट्स क्वाइट in quite different color, right? I mean, you don't have an opacity, right? That's mean it is indicated to the animal. It is indicated to the animal. Let's say again. The animal did not cross the street because it was too tired. So it किसको indicate करेगा? Is किसको indicate करेगा? Animal को, street को और tired को. As a human being, we know that it obviously animal को की करेगा, indicate करेगा, right? So इसलिए, लेकिन when you pass this data inside one machines or algorithm, it may not predict it well. So that's why the self-attention is coming up. Attention is nothing but giving the more attention to the language, more attention to the word, so that we can classify them. The it means animal. It means animal. Maybe it can be the animal did not cross the street because the animal was so tired. Like that, like this, right? That's mean it mean it actually indicate to animal. That's why this it rare is go to the animal quite dark, right? So this is the self attention actually help us to do that, to building this kind of transformer model. See, so the self attention in detail, तो बहुत डिटेल से जानेंगे हम लोग यहाँ पर। देखो, यहाँ पर दो सेंटेंस है, थिंकिंग एंड द मशीन। वी हैव टू सेंटेंस, थिंकिंग एंड द मशीन. So when we are going to convert them thinking into the vector, we may use some embedding algorithm like what to back or TF-IDF. So we are going to converting this embedding layer into one kind of vector of the size of 512. Then we have queries, we have keys, and we have values. See, notice there's new vector as smaller to dimension than embedding vector. Their dimensionality is 64, while the embedding and the encoder and input output vector has the dimension of 512. See, the embedding dimension is nothing but called 512, and the vector of the dimension is 64, right? That's mean we have one weight vector, okay, weight vector here, and also the queries. So it's actually initialized in randomly. यहाँ पर ये randomly initialize होगा. If you're coming from the neural network architecture, I mean, if you know about the neural network architecture, when you are actually initialize your weight, you may initialize it randomly, right? Then you are updating the weight using the back propagations and do the weight updation, right? So that actually happening here. The embedding vector is nothing but 512, and the weight, I mean, the dimension is nothing but 64. It's a 64 of dimensions, right? We have the queries, we have the keys, and we have the values. We have their respective kernel, or you can say filter, right? So what actually happening here? They actually calculating the scores. So what kind of scores? Attention score. What kind of score? Attention score. See here. So embedding the queries, the keys, and the values for thinking and also for the machine, they actually generate it. Now when you're calculating the value, I mean self attention value for the thinking, you need to multiply with query and also the k1. See, q1 and k1 and give you 112, and you need to also do the same thing for their q1 and the k2, and you can also give here one value that's called 96. That's nothing but your attention score, right? Okay, let's take one pen so that you can understand easily. Okay, see one thing here, when you are calculating the scores, it will multiply with q1 and the k1, this one to this one, and we also multiply with q1 to the k2, right? For the thinking word, right? But how are you calculating for the machine word? So what will be the score for that? That's mean q2 cross k2 and q2 cross k1, right? Like this one. How you calculate the score value for the machines? Now you're calculating for the thinking value for the thinking. That's mean q1 and the k1, we get here the value of the 112 and also 96, right? Same as it is again. So let's also remove this out. Okay, wrap this out. Okay, good. Now we are going to discussing about the next one. See one thing here. Okay, cool. यहाँ पर जाना है इसके बाद. Okay, fine. Okay, see, q1 and the k1 we get the value as 1 and 2, and q1 and the k2 we get a 96. That's mean see one thing. Thinking is the first word, and machine is the next word. I mean second word. That's mean when you are translating one language from the another language, obviously you get the first impression to the thinking word. Then you get the next impression to the machine word. Let's say I am a boy. So I obviously get the most higher attention. Then am, then boy, right? So that's why when you are calculating this, the thinking word getting the high attention. That's why you can get the value as a 0.88 and 0.12. But when you actually actually add them, you can get the value 1, right? That's mean this value is not greater with 1. Now the question in how can we get this 14 and also the 12? See here 1 actually they divide them with the 8. Now after dividing by 8, we get 14. But why should 8? Why 8? They actually wrote it, right? They actually wrote it by 64. Now why 64 again? Why 64? क्यों 64 है? देखो आगे जाते हैं यहाँ पर. देखो यहाँ पर हम जो इसको वेक्टर में कन्वर्ट किया ना, वहाँ पर मैं पाया था डायमेंशन 512. लेकिन हमारा डायमेंशन जो है ना, आफ्टर एम्बेडिंग लेयर वी गेट द डायमेंशन ऑफ द 64. That's the dimension of the 64 of the queries. And when we root it, we got a 8. See one thing. एक्चुअली क्या क्या बोलो यहाँ पर रिसर्चर लोग ना बहुत कुछ करते हैं यहाँ पर. कोई बात नहीं. So we got here the 64 root equal to 8. Then they divide by 1 on 2 by 8. Then we got 14 and we have the 96. I mean 12. So that's mean we get here the value of the queries is 14. That's when we got here the higher attention. Higher attention. Let's say when you're translating one language from the another language, let's say thinking mean in Hindi, let's say in Bangla it's called chinta kora, right? Chinta kora. And machine means jantro. See, when you actually converting this one language to the another language, the score value is important. I mean the sequence is important. Let's say I am trying to say that I am a student, but when you're trying to convert them into the Bangla, Ami Chhatro. That's when I is giving the higher attention. And also the sequence is also important. So that's why we gave here we give it the scores. We give it the scores. That's called the attention. बहुत important part here. बहुत important part here, right? Okay, let's keep it down. Okay, let's erase it. Okay, so that's really great. Now, then we are going to go on the next step. लेकिन यहाँ पर एक क्वेश्चन है ना, how can I get this 0.88 and 0.12? And when you add them, we get here 1. But why should we get that? Because of the softmax activation function. Because of the softmax in activation functions. So that's why we got here this kind of value, which is the addition of them two values nothing but 1. So this is nothing but one classification. I mean multiple number of sentences. That's why you're actually using here softmax. But if you have the binary classification, obviously you can use the sigmoid. So that's why you have so multiple number of features. So that's why using the softmax activation function. And based on that, it actually gives me some score value. Now the thinking value accuracy is nothing but 0.88% and the machine's value is nothing but 0.12%. See, now the fifth step. So after that, what I can do, when we actually pass the sentence to the embedding, it actually pass to the queries and you have the K1 and the B1. And then what I have, we have the Q1 and the K1 and we have the Q2, K2, 96 and 12. And we get the value 0.88 and 0.12. Then what I can do, we can use the cross multiplications after that and we get here the sum. That we actually get it in the, here, Z1. Right? We get the output in the Z1. That's in what I can do here. We first convert them into vector, then we get here the queries, we have the keys, we have the values, then we actually multiply with the weight, and after that we can get here some scores, and after converting them divide by the 8, we get here one value, then we pass it this data inside our software activation functions, and we are going to multiply with the values, right? Actually using the all kind of values, do the multiplication and get some values. Then we can pass it inside one vector that's called the sum, right? So now the question arises, how can we multiply this weight and the queries and values? See, that's called a multi-matrix calculation of the self-attention. See, x is nothing but one vector. X is nothing but one vector. So the dimension of the x is nothing but called 512. And this is the weight, the vector of the 64 size. Then when you actually do the matrix calculation, we get here the value of the 64. We get the value of our Q, I mean our queries. Then again, when you actually calculate, when you actually calculate this matrix multiplication with the weight of key, weight of key, then we get here the K, same as it is, right? Then what I can do, we are going to pass this data inside one softmax activation function with having the transformation, transform of the our matrix, and we actually divide it by 8 because the filter size is nothing but called 64. Then we need to pass in inside one software activation functions, and after that we need to also multiply with, and we get here the sum. So this is nothing but our full step, right? Now this is nothing but for the head 2. Let's say we have one sentence. So maybe we have the attention head of the 0 and attention head W1. But when we have the more amount of sentence like the thinking machines or I am a student, I am Chandu, I am Nishudar, like that means there are so many head. We discuss about just one single head. One single head. If there is a multiple number of head, obviously there are multiple number of head. I mean multiple number of attention head, right? Then what I can do, we are going to calculating them. The calculating the attention separately in the 8 different attention head. 8 different attention head. That's mean they actually talking about that here. There should be the 6 encoder, the 6 decoder, and 8 attention head. 8 attention head. That's mean they actually calculating the attention separately in 8 different attention head. That actually discussing about in their research paper. Right? See one thing, if we do the same attention calculation we outlet about just 8 different time with different weight matrix, we end up with the 8 different jet matrices. That's when we got here 8 different jet matrix. Now what I can do, we are going to pass this jet matrix inside one feed forward neural network, right? But before that, you can see concatenating all the attention head. So when we get this attention head, we need to also concatenate it. हमको क्या करना पड़ेगा, यहाँ पर ऐड करना पड़ेगा सब लोग को. Then what I can do after that, we are going to multiply with this full weight to the weight. Then we get here one single jet matrix. Then we can get here one single jet matrix. So this is the full overview of the multiplication. See, thinking machines, it will convert them into the embedding vector, and we have the weight of the query, the key, and the value. Then we multiply it, and we get here multiply it. Then after that, we are going to calculating the score of that, and after that we divide them 64 root, that's mean 8. Then we're going to pass in that inside our softmax activation function, and after that we got here our attention score. Then we are going to multiply with the value. See value. Then we got here our sum. I mean sum attention head. Then what I can do, we're going to concatenate it, and after that again we are going to multiply with our weight that is randomly initialized, and after that we get our jet. Well, now based on that, it actually give here the attention score. Now based on the attention score, it actually initialize that. I mean it actually identify that which one is more accurate, the animal or the street or the tired. Obviously it should be the animal. So this is how the attention mechanism actually work here. Now this is one another part. So why should we do the positional encoding? See here. So this is the another part that's called representing the order of the sequence is the positional encoding. Okay. See, we have the 6 encoder layer, right? So when we do this part, we need to also do the positional encoding. Now the question is, why should we need to do the positional encoding? Again, one important question. See, I am trying to convert one sentence from English to Bangla. Let's say I am Mishudar. That's mean I के बाद aim होगा, aim के बाद Mishu होगा, Mishu के बाद धर होगा, right? That's the sequence. लेकिन when you trying to translate them in the English to Bangla, আমার नाम मिशुदर, sequence में भी carry, position में भी vary, right? लेकिन मेरा नाम है मिशुदर चंदू, इसका बाद मेरा आउटपुट आया चंदू धर मिशु. It's quite different. That's why the positional encoding, the position of the sentence is quite important. That's why when you're trying to encoding them, the position is mandatory. Because when you're trying to translate from the one language to another language, position तो बहुत vary करता है ना यहाँ पर. इसलिए we are going to using here the positional encoding. ध्यान से सुनना, right? So then what I can do, we are going to pass this input to the embedding layer. Then we also add here our positional encoding. Now based on the positional encoding, we can get here some score. You see, the Z is the first word, that's why the attention score is 1. Then you have the switch, we have the lower attention, then the edu10 is have the some -1. That's mean is the last one. is the last sentence, right? So this is how actually attention mechanism work in here. Now we have one residuals block. So now we're going to see that what is actually residual connections. Maybe you heard the name of called the RASNet 50, called the RASNet 50. My handwriting is so bad. So RASNet 50 is nothing but one architecture in the transfer learning. Maybe you hear also the name called the RNN, right? So in RNN, there are some residual block. That's one block, second block, third block, and the fourth block, right? You're going to pass the data from one layer to another layer like this, right? Also, you can also pass the data from this layer to the this layer. Then you can, what you can do, you can do the cancellation. This is how actually residual connection actually work. That's when you can also cross them, or you can cancel it, right? So this is the residual connections. Now in this way, in this self attention layer, you can also do the residual connection. That's, you can also call this as a dropout. When you are trying to build one RNN or the ANN model, right, based on the accuracy or the problem or the overfit or the underfit problem, you may do the dropout. So in residual connection, you can also drop out in the self-attention layer. Let's say I'm going to pass this thinking word and the machine word to the self-attention. Maybe my self-attention is not required, or it's not giving the goal result. So I can also do the dropout here and do the normalizations. Same thing we can do that here. We don't need to do the forward uh, neural network, feed forward neural network. We can also drop out that. So that's called the residual connection. That's mean you can jump from this layer to this layer, right? Then again this layer to this layer. You don't need to do this out based on the accuracy model. So this is how actually residual connection actually work. So what I can do, we can simply pass this thinking data and machine data to our self attention. If the self attention is not needed, we can simply drop this, or we can simply cancel this. So this is how the residual connection actually work. Then what I can do, we can do the simply call the add normalizations. Let's call the add normalizations, right? Okay, so after that, what I can do, we are going to simply pass this data inside our layer normalization function, and it will pass this data again to the feed forward neural network. So this is one encoder. This is just a one encoder. Now the question is, what actually happening inside this decoder? What actually happening inside this decoder? See, we have the 2 encoder right now, but in the research paper they actually mentioned the 6 encoder. So but just for the testing or the discussion purpose, they actually see the 2 encoder. Now we know that what actually happening inside the encoder, but in decoder what actually happening? Let's see. In decoder we have one self attention and also the self attention in the encoder, the add and normalize function here, and also the add and normalize function here. But it have one extra layer that's called the encoder decoder attention. So what is actually encoder decoder attention? This is also one self attention. So when you pass this thinking and the machine data inside your encoder, it will pass the data from the one layer to another layer. It will pass the data inside directly to the encoder and the decoder attention. It's not passing this data inside these self attention. Again, one thing, when you pass this data inside one decoder, it actually passes data inside your encoder and the decoder. Then encoder and the decoder pass the data to the decoder 2. Then it will pass this data to the linear and the softmax. Then this data of the output again go back to the decoder. See one thing, let's say go to the pen. Okay, I am trying to wrap this out. Then we're going to discussing about what actually happening inside this encoder and the decoder, and how you pass the data from one layer to the another layer, right? Just I'm going to wrap it out. Give it some time. Okay, let's take the pen now again. Okay, see, when you are trying to pass one sentence, from the one layer to another layer, that's mean you're going to passing this data from this layer to this layer again, right? This encoded and the decoded attention, it will pass the data to the decoder 2 and the linear functions and also software activation function. Now you can get one output. Now see, for the thinking word, maybe you get the output, you may get the thinking output in a Bangla. Let's say chinta kora, or in Hindi language sochna, like that. So now when you get the output for the thinking, now you need to also get the output for the machines. Then for the getting the output for the machine, you need to pass this thinking data inside your self attention, inside your self attention. Now this data is passed to the self attentions. You can also do the residual connection, or you can drop out it. Then it go to the add normalization, again encoder decoder condition. Then again it will pass to the self attention layer again, like this one. So this is how the encoder decoder actually work. Again, one thing, when you pass this thinking, it usually store inside your encoder, inside your encoder, inside your encoder. Then it pass to your decoder. This pass to the decoder, and when you decode this data, and you can get the thinking value as output, right? I mean chinta or sosna. Then again for the next word, you need to also pass the data inside your self attention layer. So this is how actually encoder and decoder actually work, right? So now let's see the decoder side in a graphical format, see in animated way. So this is our input in Spanish or the French language. I don't know what is the language it is. Then we need to convert them data into the embedding layer. Then after that, it actually embedding them with some time signal, because this is one it have a residual connection. So that's why based on the time stamp, or to pass the data. After that, it will pass inside one encoder. Again, one encoder, I mean 6 encoder. Then we are going to do some multiplication on that. And after that, we pass this data inside your one decoder. And we are going to pass this data to the linear and the softmax. And we get the output. Again, we get the output. When we get the one output, then we're going to pass this data inside one decoder. Then again, get one value. And after again, we're going to pass this data inside one decoder. Right? So this is how the encoder and the decoder side actually work here. So you can see this is the final of the softmax layer that you can see here. We get here the value. So this is how it actually work, and that's the complete graphical user interface of that. See, the decoder step have the 6. So see one thing, J Swiss encoded, pass the data from here. When you pass the data I, we get the first value of the I. Then we're going to pass this data to the again to the decoder, and you get M. Then again, see one thing here again, I we got the output of the I. Then we pass this here, and we got the output of the M. Then again we pass this data inside the decoder, and we pass here a, and again pass the data inside the decoder. Then we have got a value as a student, see a student. Then again we're going to pass here, right? Like this one, I am a student, right? So this is how this is the full the transformer actually work in order to translate one language from the another language, right? If you have any query about the transformer, you can also leave a comment below. And if you need any tutorial regarding some topics like Google Bird, so Google Bird or bird, not bird, BERT, or also one language model. And if any kind of project you needed, you can also comment below here, so that I'm trying to make this out, right? So that's it for today now. Hope you enjoyed this tutorial, and make sure to subscribe to channels, and don't forget to hit the bell icon, right? So I'll be back with another tutorial. So till then, take care, and bye bye.